I did my project of the physics of a soccer free kick. My motivation for the project, I've been in love with soccer since I was a child, and back when I played, I heavily practiced free kicks to learn the technique perfectly. I remember very interesting free kicks I've seen throughout my life, and I wondered how they actually work. I think the drag and viscosity through the air be a major factor in how the ball moves when kicked, and I intend to explore this concept with a project and a study of a one-of-a-kind free kick, which I saw live. My question is how net force, acceleration, velocity of the ball changes and approaches the back of the net. My hypothesis for this project is how as the ball travels further where it's kicked, the net force, acceleration, and velocity should decrease as the forces of gravity, drag, and viscosity oppose the vector velocity and the overall motion of the ball. The situation I've chose to model is an indirect free kick, which is like a normal free kick, so the ball must be touched before the attack team is able to score with it. It's a word for things like descent, playing in a dangerous manner, or the keeper picking up the ball passed back to them by their own team. They're highly rare and unusual in the box of the defending team. So here is the free kick, which I have chosen now. So even among indirect free kicks, this is a very atypical example, because normally what will happen is the one player will simply roll or tap the ball for the other player to shoot immediately. But here it's a trick play where the attacking team fakes tapping the ball several times to catch the other team off guard when it's actually shot. The ball used here is the official ball of the J League, which is the Adidas Bazooka, which is 0.457 kilograms and 0.11 meters in radius. The system scheme of the instant the ball is struck is that the soccer player applies a force onto the ball. Additionally, the earth exerts a gravitational and normal force onto the ball in addition to a friction force being exerted on the ball. When the ball is traveling through the air exerts a viscous and drag force onto the ball, and the earth exerts a gravitational force on the ball. The instant the ball is struck, the normal force of the earth and the ball and the gravitational force of the earth and the ball are in balance. There is an applied force of the soccer player onto the ball, which is upwards and at an angle with the ground. And there's also a friction force of the earth and the ball, which opposes the motion of the ball initially. When the ball is traveling through the air, there's a drag force and a viscous force that the air applies onto the ball, which opposes motion towards the goal. Additionally, there's a gravitational force of the earth and the ball straight downwards. For the energy pie charts, initially it's all potential energy because the ball is at rest. Then some of this potential energy is converted to kinetic energy when it's kicked, and the force of drag and viscosity then begin to act as internal energy on the ball. And overall, the energy will decrease due to the loss of energy to resistive forces. So I modeled this free kick in Tracker, and I found that the acceleration peaked at the frame after the ball was struck at the player's foot, which was and it peaked at 696.6 meters per second squared, while the velocity peaked one frame later at 59.9 meters per second squared. There's a general negative trend for acceleration and velocity, but there are strange peaks throughout both graphs. I also calculated a net force versus time graph by taking the acceleration and multiplying by the mass in Excel. And the peak force is the same as the peak acceleration, which is 318.34 newtons, and it's just after the ball leaves the player's foot. And there's a general negative trend of the force over time, which is due to resistive forces likely. And there's also the same characteristic peaks as in the acceleration graph. And as the ball initially moves due to applied force on it conceptually, and then it initially overcomes a static friction with the grass. The ball then lifts off the ground, and the gravity downwards reduces the y component velocity, and thus the total vector velocity of the ball. The ball also must exert force on the air to speed up, which results in a force back on the ball, which is the drag force. And there's also an additional viscous force, where the ball drags air with it and rubs each layer of fluid to reduce the relative sliding, and it works to reduce speed as the ball travels towards the back of the net. So limitations of the work overall is the video quality is very choppy at times, and the frames jump around due to the blurriness of the video, and the ball can be kind of hard to follow, which explains the strange peaks and valleys found in the graphs even after the applied force was done. A better camera of the goal would likely lead to better data. In addition, the camera is at a strange angle, but because it was a vector velocity, it should work just fine, but it could impact the data slightly, result in some of these peaks. And here's my works cited. Thank you for listening.